the Industrial Planners. Welcome to the Industrial Planners seminar. It's a great pleasure to introduce Dr. Vasileios Ioannidis. He's an applied research scientist manager in Amazon AI. And he's an expert on deep learning on graphs. He got his PhD from the University of Minnesota. His advisor was Yorgos. And he's going to talk about research and development of LLMs and GNNs.
Yeah, thank you very much for the kind introduction. And also thank you very much for the invitation. I am really glad to be back here and in my alma mater, where I can present this part of our research. So in high level, the structure of the talk will be, I will first introduce some basic concepts on graph neural networks and graphs. And it will be actually most of the talk will be regarding actually introductory on graph neural networks, and I will also dive deep on a few research projects we did in Amazon with application of graph neural networks, but also more specifically how can we combine language models and graph neural networks, which is language models practically process language, right, and text, and graph neural networks process the graph data. But we will go into more detail shortly. So the research we are, 1 second. So the research we are doing in general in graph neural networks and language models can be divided into two pillars. One is about model performance. So what can we do to increase model performance? And also, what can we do to have more scalable graph neural networks and training and inference of these models? So scalability is really important for us in industry. The reason is that, we want the models to save costs practically, right? So we don't want to spend a huge amount of dollars in order to train or do an inference of the model. So that's why we are focusing on scalability. But moreover, and also we want to do things fast, right? And also we're interested on model performance. The reason is obvious, right? So we want to increase the output of our models, so the performance output of our models. And here you can see like a lot of works, which I will not go into today. Our work today will be mainly about language model GNNs for graphs with rich text features. And this is the research topic that I will present today. But before that, I want to give you an overview of graph neural networks and graph data. But if you want, you can find all this research is published in my website, so you can find some of these things. So let's start by saying that graph data are in a lot of different domains, and actually also language and text data in a lot of different domains. For example, drugs and molecules can be interpreted as a graph, right? So the way practically the molecules here are comprising a specific drug, right, can be and have specific bonds that connected the atoms here, can be represented in a graph structure. And also, as you are all aware, so social networks can be seen as graphs, right? So nodes here are the people, and the relationships among the people can be seen as edges. And also you may have multiple types of relationships connecting to people, which gives rise to what we call as heterogeneous graphs. And also you may have even knowledge graphs. So knowledge graphs is a form of actually a database. Database is a store of knowledge in the form of a graph. So practically, for example, Barack Obama was the president of the United States. This fact can be seen as an entry in a knowledge graph, where practically Barack Obama and the President of the United States are two entities in this knowledge graph, two nodes, and is practically an edge. And these knowledge graphs have billions and billions of nodes and millions of relationships, millions of relationship types, which gives rise to trillions of edges. And these are actually very common way to store knowledge. And finally, we have e-commerce networks, which will be also a little bit the focus of this talk today, because e-commerce networks practically talk about how a product can be bought by certain customers, right? And a seller can sell a specific product. So this type of heterogeneous relationships can be captured in a form of a graph. So what do the customers buy, for example, for given their, for example, preferences? So this is an e-commerce network. And besides actually this rich graph structure that we just explained, a lot of this information, these networks, these graphs, are accompanied also with text. So what does this mean? For example, an ASIN means product. A product can have a product title, can have a product description, and this is textual information, which we are trying to encode in some way, in some kind of vector representation. So this goes about graphs and where can we find them. But what are some common GraphML tasks, right? So what are, let's say you are given a graph, right? So what ML tasks you can solve on this graph? So here you can see a typical graph. Here you have like different nodes, right? And you have relationships. Even it can be a directed graph or an undirected graph. In this case, it's a directed graph. And in general, you may have like node prediction tasks, which means, for example, we are trying to predict whether a node in a social network is a fraudulent user or node. This is like a node classification problem. A classification problem, let's say a 0-1 prediction, you want to predict, is this a fraudulent user or not, right? So you want to predict a label, 0 or 1. And this is a level, a node level task. You may have a link prediction task, and a link prediction task involves two nodes here in the graph. So what does mean a link prediction? I have the following problem. So is this node with that node connected? So should I recommend, for example, Georgios to Vasilis as a friend, right? So in the friendship relationship, right? And this, the reason we call it link prediction and not graph construction or graph reconstruction is we want to predict a single or multiple links in the graph. We may not want to predict all the links in the graph. So, and here we are talking about knowledge graph completion problems. So you have a knowledge graph, the graph database I was referring to earlier, and you want to complete this knowledge graph, right? Or you have recommendation systems, or even you can formulate drag repurposing problems under this context. And finally, you may have some subgraph prediction tasks. So you are given 3 nodes and you want to predict whether these 3 nodes together form a fraudulent sub-network in your graph. Or you may even have like graph predictions that involve the whole graph, right? So essentially you want to predict a label 0-1 for the whole graph altogether. And this is typical in molecule property prediction. And yeah, so this is like, you can see there is a suite of GraphML tasks that you may be interesting to solve, right? So how do you solve them? So you can solve them in multiple different ways. And today I will talk more specifically about graph neural networks. And graph neural networks actually are deep neural networks that learn representations of nodes, edges, or the whole graph. So what does this mean? Representation means like it's a vector representation. So imagine you want to learn a vector for each node in your graph, right? So you have essentially a d-dimensional representation of each node in your graph. And you learn this d-dimensional representation by this, what I call here GNN, graph neural network for short. And this acts as an encoder, okay? This will encode the information of the graph, and the information that I mean here is the edges and the possible features. And you will encode them in these vector representations. And then these vector representations will be fed to a classifier that will predict, in this case, what is your favorite basketball team? Is it the Knicks or Golden State Warriors? So in a high level, this is practically how it's a high level architecture, right? But how it works in practice, we will see right now. So practically, it works, the GNN works with a framework we call message passing framework, message passing system, okay? So the message passing framework practically, as the word suggests, relies on the nodes in the graph exchanging messages. But what does it mean more formally? So as I said, the graph neural networks can be interpreted under the message passing framework. And here, let's say we have a central node V1 here, right? And we want to learn, and we have actually 5 nodes in this graph, in this toy graph. And each of these nodes is associated with a vector here. So this vector may capture, for example, attributes of the node, like, for example, the age of a person, the education level of a person, And all of these things can be stacked into a vector, okay? And this represents H1, which are initial vector. And we have 5 vectors and 5 nodes. And you see we have 4 connections of these nodes to the central node. So practically how message passing works is the first thing we define is a message function, okay? So this M of superscript L, for now, ignore the superscript L, but this M function is a message function, right? And it will take as an input the source vector, for example, H5, and the destination vector. No, I'm sorry, I think this is the destination vector and the source vector. So H5 and H1, and possibly some information you have on an edge. So the information on the edge can also be used as an input to this function. And this function actually is a learnable, it's a learnable function. It has, for example, some learnable matrices, as neural networks typically do, that can be optimized end to end. And then after this will calculate a message, the message from this node to that node. And then you need to have a reduction operator. In this case, we just sum all the messages that come from the neighbors of node, for example, V. And this will be aggregated into a single message vector, okay? And this will be the message vector of node V. So it contains all the aggregate messages of his name. So in this case, we will also define an update function. So an update function U will take as an input the message vector and the vector, the H1 here, the vector of the node in the previous, let's say, iteration. And it will output the representation of the node for the next iteration. So when I'm saying iteration here, I really mean layers. So this will be stuck together to form a GNN layer. So this, I just described the operation of what happens in a single GNN layer. And this will be actually stacked for the second or for the third GNN layer. And so some initial version of this model, of this formalisms can be found actually in this paper. But I think what is interesting here is that these U and M functions, as I said earlier, are learnable functions. So they are not predefined by a user, but they are actually, I will show you some instantiation of this function in the next slides, but they contain learnable matrices, W, that can be optimized end to end, but in a graph neural network fashion. So what is a very common, one of the first graph networks is called the graph convolution network. And practically the message function in this case is just the summation of your neighbors and neighbor embeddings or your neighbor vectors, right? So what you can see here is that we sum over all of the vectors in the vicinity of a node, right? And we adjust them by the average, by the inverse of the degree of node V. And this will be the message function. And as you can see here, this specific message function is not learnable. But what we can see is that the update function contains this matrix W that multiplies actually the message vector. And then we apply the element-wise nonlinearity phi that can be like the sigmoid or something else. And finally, we get the vector for the next layer. And as I said, this can be stuck together. So this can be, for example, so this phi can be the ReLU function or other ones. So interestingly, actually, this kind of message function has been recovered in a lot of works. And one of the works is work of my advisor, Professor Ioannidis. So when they have this paper where they are trying to apply sparse structural equation models to infer generic regulatory networks, right? And the sparse structural equation model practically tells you that the signal that you are trying to estimate, or the vector that has been talking about here, is governed by an equation that looks very similar to that. Practically, you multiply the adjacency with the signal, and you get that your next, let's say, your model is practically, you are trying to average, you're trying to get close to the representation of your neighbors, right? Which is practically what this message function tries to do. And there have been extension of this work by Professor Sen, Yannick Sen, that was another one of my colleagues, on applying this on nonlinear function as well. And this work in KIP in SCLR actually have introduced this W learnable matrices here and optimized this neural networks end-to-end to solve tasks like node classification. So yes, so that said, so graph convolutional network was one of the first works in this, and it's an interesting paper to read. And there have been a lot of follow-ups to that work, such as the graph attention networks. So the main difference of the graph attention networks comes in the message function. So what they say here in this paper is that not all of my neighbors have the same weight, right? So imagine I have, for example, 10 friends. I will not give to all of my 10 friends the same weight when they tell me their opinions. To some friends, I will give more weight and so forth. And this weight can be is this learnable scalar here, alpha of VW, meaning you want to learn an attention weight, as they call it, between node actually 3 and node 1 here. And as you can see, we have multiple lines, meaning that you want to have a multi-head attention. So this concept is borrowed actually from language models, where they have first introduced these attentions, but then they realized that it works pretty well also in graphs. And what is this attention weight? Practically, in this expression here that you can see that I have highlighted here, this expression, practically you are trying to find how aligned are the vector V to the vector W after you apply some learnable matrices W. So how aligned are these two vectors? And this will tell you, for example, how much attention you should give. And all of these are learnable with respect to your task. And then you have the update function that is actually the same update function as we saw in the previous slide. This is in this paper by in ICLR again. And what we said here is practically we want to give different weight to different neighbors, right? But the next extension is actually what happens when you have heterogeneous graphs. And what are heterogeneous graphs? I alluded to that a little bit earlier. They are graphs where they have multiple node types and multiple edge types. So for example, this is a typical knowledge graph. This person, Mikhail Baryshnikov, is a citizen of the United States. He was educated at this university and was awarded this prize. So these are all different node types, and these are all different edge types, okay? And what they are saying here in this work is that actually messages should be weighted based on the relationship type. So what does, for example, in a social network, you could imagine my friendship will have, my friend's weight will be different with respect to my family's weight or to my colleague's weight. So all of these represent different edge types, and you want to model them differently. This is why this learnable W matrix now is weighted by R, where R is the relationship type. And again, the update function is similar, the same update function as we saw earlier. And here, the WR and this WL are learnable vector matrices that are optimized end-to-end. And as I said so far, I have been talking about basic layers of graph neural network architecture. But an L layer graph neural network is comprised by stacking these capital L layers one after another. And finally, you will get this vector representation HV of L for all nodes in the graph, right? So as I said earlier, so GNNs will recover some vector representations for all the nodes in the graph. And these are the vector representations we recover. And now we can use actually this HV of L in downstream models, and we can train this with any loss function. So what are the downstream models and the downstream tasks? So I want to give a little bit more formalism on what I was saying earlier as node classification, right? As we said, we can classify nodes in a social network as fraudulent or not fraudulent. And a node classification task is trained by applying, for example, by transforming with a vector, with a matrix W, this HV of L, the vector representation, into essentially a probability distribution right? And we want to align this probability distribution with the label V by applying a cross-entropy loss function here. And this is the loss function, for example, for node classification, we just attach this loss function to the GNN and we'll train everything end to end. And the GNN will learn representations that will try to optimize this, to learn this probability distributions that are close to this ground truth distribution. Another very important task is link prediction with GNNs, right? And the GNN here is supervised to align the embeddings of connected nodes. So what does this mean is I will learn these embeddings between nodes V and nodes W. And in the end, what I want to do is pretty much align embeddings of connected nodes. So I want embeddings of connected node to be similar, whereas I want embeddings of disconnected nodes to be far apart. Of course, you could argue that the GNN architecture by itself, based on these message operations that I was showing earlier, can implicitly do that, right? Because this model says that, okay, my next layer, my next representation is the average of my neighbors. But here you are trying to enforce more of this supervision in the loss function. And here I have something I call positive edges and negative edges. Positive edges in the graph are actually edges that exist in the graph. So if, for example, Vasilis and Yorgos are friends, I want their embeddings to be close, right? And if Vasilis and Daniel are not friends, I want their embeddings to not be close. And this is what is captured in this loss function practically. And this also, and the next loss function I wanted to introduce is the graph classification loss function. So the first when you want to apply what they call a readout operation, so practically it's a function that will take as an input all the embeddings of all the nodes in the graph, and it will output a single embedding, which will be the graph embedding. And you can do this in a lot of different ways. That's why I keep it as a readout function. And finally, you want to align this graph embedding to a label distribution, but now the label distribution is at the graph level, not at the node level anymore. And then you want to do some soft classification. So these were like the three most popular actually loss functions that you use typically in graph networks, right? So the way you solve these problems is you try to understand how your problem maps to one of these three core, let's say, components: link prediction, node classification, or graph classification. And then you try to understand what architecture works best for your problem. So today, I reviewed with you three very basic architectures, which is, for example, the graph convolutional network, the graph attention network, and the RGCN, the relational graph convolutional network. And yes, so this is so at this point, I would like to compare a little bit some positives and negatives of GNNs with traditional approaches. Julia, do you have any water by any chance?
I can get you. So,
it's really early for me. California time. So, how GNNs compare with traditional approaches? So, first, GNNs are versatile in the sense that they compute embeddings that both respect the graph structure and the original node features. So when I'm talking about original node features, as I said earlier, I mean, for example, this person is, their occupation is an analyst, their education level is master, their age 35, their sex is male. So practically, you encode this in a vector representation, and this is your input vector representation, right? The feature of a node. Then here you have books, right? To recommend to users books. And this books has a title, has an author, price, and so forth. And this also can be stacked into a vector, and this will be your book feature. So you have a user feature and you have a book feature, right? And then you have the graph structure that connects these two. So practically, GNNs is an easy way where you can encode both the graph structure and the features into a single representation vector. All right, thank you a lot. And for example, methods like, for example, the Laplacian eigenvector decomposition will decompose your graph matrix to Laplacian eigenvectors, and these Laplacian eigenvectors can be thought as vector representations again. But this method, for example, would not take into account features. Of course, there are other ways that you can encode both the graph structure and the features, possibly through a loss function that tries to align the representation with the two. But this is just a way, an encoder that can achieve both at the same time. And GNNs are nonlinear, right? And can integrate topologically distant information in nonlinear fashion. So what does this mean? Is that imagine my final representation for node 0. Okay, my final representation for node 0 will, if I have a 2-layer GNN, what it will do is will account for, in the first layer, I will account for all the messages of my one-hop neighbors, right, of nodes 1, 3, and 4. But in my second layer, I will account for each of these nodes in my previous layer. I need to create the representations, right? For node 1, I need the messages from node 5 and 6. So practically at the end, for node 0, I will recover all these messages that can be, and further, these messages will be combined in a nonlinear function. And this combination will be learned, right? So it will be learned to optimize a specific objective function that I showed earlier. And yes, and they are also task aware, right? So GNNs can be trained with the downstream classification models end to end. And this again is to be constructed with two-step approaches. So some traditional methods may encode, for example, the nodes of the graph and the edge, and the nodes of the graph and the features into a vector. Right, and then with this vector that has been already learned, right, we'll try to learn a new classifier model in order to find your favorite basketball team. GNNs, on the other hand, can be trained end to end. So the vector extraction method and the classifier can be trained end to end. And this is another advantage of GNNs. And again, I want to say that this is not an advantage of GNN versus all other methods, that because a lot of other methods can also be trained end to end, and there are formulations that can be introduced. But these are some benefits of GNNs. And finally, also the GNN models are inductive. Actually, this is a very important problem for us, let's say, in industry. So imagine you have trained your GNN model on this graph of these four people. Okay, so you train the GNN model, you learn some parameters, you learn the model that can do inference, right? So imagine a new node comes in the graph and connects somehow to your basic structure. The GNN model, without learning anything new, you can apply the same GNN model you have applied here, and very efficiently get a prediction for this new node. On the other hand, like for example, eigenvector decomposition methods, although they can be applied to do incremental inference. So what happens when a new node comes in the graph? This is, let's say, in this way we have a more efficient way to do it. Let's say, and for the efficiency, I will. So for the efficiency, I will not talk in this talk, but we have other talks that explain why GNNs are efficient. But in short, GNNs are efficient because they rely on this message passing operation. So this message passing operation I was telling you earlier, that what does it mean? That to calculate a representation of a node, you simply need your neighbor's representation. This is actually something that can be implemented very efficiently if you talk about billion node graphs. So you can break a billion node graph into a lot of smaller graphs by only taking into account your small neighborhood that is of interest to you. In this case, for example, 2-layer GNN, 2-hop neighborhood. And you can break these computations and can perform this inference in a very efficient manner. And And at this point, I wanted to tell a little bit about how can one start developing GNNs or can start entering like the graph-neural network field and coding GNNs. So to that, I would really recommend DGL. So DGL stands for Deep Graph Library, and it's an effort that started in Amazon Web Services, and it has been continuously developed and further extended in with multiple contributors all around the world. And it has a lot of tutorials that can get you started with a lot of simple and basic models. And you can just take this library and the models and tweak them to your own purposes, develop new models and solve new tasks. And it is also very efficient. It can scale to billions and tens of billions of edges. So the DGL is also something that has allowed us to perform a lot of external collaborations, because DGL, as I say here, is open source. So this means that everyone can contribute and everyone can see what we are building there. And I can tell you that the DGL is what we use really internally also even in Amazon. So practically, we open source this effort so that we can both benefit from the community and build a better product, right, in Amazon, but also at the same time benefit the community. And here is the release history of DGL. I don't think we need to go into this detail, but let me just say that it is a mature product that you guys can like take a look, and this is the website, so dgl.ai. Yes, so now we go into like the more, let's say, meaty part of this talk, which is about language model GNNs, right? And here, practically, we want to talk about how to combine both language and graph-neural network models. So, but why the language? So I'm pretty sure you're all aware of like the advances recently with ChatGPT and like OpenAI and all of these things, right? So practically, around 4 or 5 years ago, there was like some work like BERT models, right? Bidirectional models, transformer models. And in general, the transformer models revolutionized the field of language processing, okay? NLP, what it was called. So going from RNNs to the transformer models has increased the performance tremendously. And then there was a lot of other subsequent efforts that led finally to what we call today ChatGPT, right? But at the same time, in a lot of popular industrial graphs, we have, besides a multi-entity graph, so practically imagine we have the buyers, we have the products, we have the sellers, all of these are connected in a heterogeneous graph. We have reviews, for example, that this customer reviews this seller or reviews this product. And so you have like multiple edge types, right, and multiple node types. But also you have like queries, right? So imagine you have a blue wedding guest dress, right? And you type this query here, then you see a list of products, you click something. So this click represents another edge, for example. And here you may have, for example, a product, and the product has a title, it has a description, it has a price. So practically a product has a list of features, right? But we always see that this title, the description, the query, the text of the query are very, very important attributes that we need to encode well, okay? We need to find a representation for these textual features that is very, very informative, okay? And this gives rise to a multi-entity heterogeneous graph with rich textual features. And we also even have like reviews, right? So we have reviews, the reviews have a text, right? So this is an awesome product, I love it, or this product is not nice, or this product is defective. So all of these are very important features, right? We want to capture them. And not only in this type of graphs, but also you have citation graphs, right? So you have a paper cites another paper, and you have the abstract of the papers, right? Or the title of the papers. So the title and the abstract are very, very important, actually, features when you try to predict the citation, right? So, for example, you can clearly say that, for example, a biology paper will not probably cite a civil engineering paper, right? So, and this prior can be captured from if you embed well the text. And even you have like co-purchasing graphs. and here you have the title of the product. So text graphs are very, very common. And yes, so to take a step back, so how typically people deal with text, right? So you encode the text using some model like the BERT model, the bidirectional encode transformer model, which is, as I said, is so I'm sorry I don't have the citation here, but it is a very famous paper that talks about how you have a bidirectional transformer model. And here, this model misses the structure. So practically, it will embed this review into a vector, but it will not know, okay, what are other reviews that the customers have also typed for this product. So it will only account for the actual text of this review, but not of neighboring reviews, let's say, right? And this is what this model misses. Then we have the relational GCN model that we saw earlier. And as we say, we have the GNN encoder, and here we have a structural prediction decoder, practically link prediction loss. And this model, again, is the multi-relational message we discussed earlier. And this will exploit the graph structure to generate a multi-entity graph-aware representation. So this representation will be graph-aware, but again, will not be text-aware, right? So we would like eventually to build a model that achieves the best out of both worlds, right? And to do so, we have developed this architecture called Language Model GNN architecture. And practically, imagine so instead of starting with the initial node feature, we start with initial text. So we have the product Nike sports shoes. And then we apply a transformer model that is a common language NLP architecture in order to get an embedding vector that is then fed into a GNN model and practically as an input feature to a GNN model that applies this layered architecture I was discussing so far, right? In order to get finally a single embedding that can be optimized for link prediction again. And so practically we stitch together these two models, but we faced several challenges. The first one was related with efficiency, and the reason is that for a specific node, typically if you do the two-hop neighborhood expansion, you may end up with millions of source nodes, right? So what does this mean? So if I am following Justin Bieber, right? Then the two-hop neighborhood of me is all the neighbors of Justin Bieber that are like millions, right? So practically, you can clearly see how very easily you can go into an explosion of your two-hop neighbor. So what does this mean? So this means that I would even to calculate a single embedding, my own embedding, I need to calculate all the embeddings of the neighbors of Justin Bieber. So which means I need to do millions of passes for these very expensive transformer models for a single source, for a single output, right? And how many times I need to do it? How many nodes I have in the graph? I don't know, millions. So millions times millions. So it's not practical, right? And so even like 400 passes of a language model for a target node, it takes a lot of time. And we are talking about trillion edge graphs. Typically in industry, we're talking about these numbers. So there were a lot of challenges we needed to face with respect to efficiency. And to do that, and you can see in the paper what we did, practically, we can do some kind of subsampling in the neighborhood, some kind of, we try to find the most important node to sample in the neighborhood, and some tricks like that. And also we faced also effectiveness challenges. So what does this mean? This means that if you stuck together this architecture, doesn't work well out of the box. And I will, in the next slide, I will show you what we did for effectiveness. So for effectiveness, we devised a strategy called stage-wise fine-tuning of the language model GNN. So the first thing we want to do is we want to do a graph-aware pre-fine-tuning of the language model. So practically, what does this mean is we try to optimize the language models, the transformers here, on the graph structure, okay? So we're trying to make the transformers predict similar embeddings for nodes that are connected in the graph. So we call it graph-aware pre-fine tuning. The next stage we do is warm starting of the GNN model. So which means practically when we start training this model, because the first part of the architecture here is well trained, and this part is practically random at the beginning, we will do warm starting. So we will not propagate the loss to the well-trained part, but we'll only train for a few epochs only the first two components. Finally, we want to do this end-to-end fine-tuning that will to fine-tune the whole architecture end-to-end for the task we want to predict. And this is the three-stage approach, which is one of the things we do in this paper. So the paper also includes a lot of other actually things that you can read here. And if you, I can also send you the slides so you can contact me later for the slides. So the stage-wise fine-tuning practically is effective across tasks. So here we have the OGBN archive, products, and Yelp. So these are practically benchmarks that people are using for node classification. And what you can see is that the last row that contains all these three steps of stage-wise fine-tuning across the board can improve a lot the performance. Right, and here the baselines are different configurations of the model, with or without stage-wise fine-tuning, or even some other kind of baseline. So practically, here, let me also state that our architecture here is agnostic on the specific GNN model you use, and also agnostic on the specific transformer model you use. That's why we call it an architecture, not specifically a model. So it is a framework that you can plug in any GNN encoder you want or any transformer model you want. And this was about node classification. And for link prediction, we can see again the same kind of, we can establish the same kind of logic that practically the stage-wise fine-tuning can achieve the best results across the board. And yes, so this was in this paper practically, so we introduced this framework, right? So this framework came with a lot of challenges we needed to solve in efficiency and effectiveness. But following up this framework, we performed some research with some of our interns about how we can solve specific use cases. And one specific use case that we have in across a lot of industrial applications is you have multiple machine learning tasks or applications, right? But you have a single heterogeneous graph. So what does this mean? So, for example, we have a single graph in Amazon, let's say, right? But we have a lot of machine learning tasks we want to solve. We want to solve fraud detection, we want to solve recommendation systems, we want to solve a lot of different machine learning tasks. So we have a lot of machine learning tasks in a single heterogeneous textual graph. And these different GraphML tasks can be formulated as node classification, link prediction, graph classification, community detection, or anomaly detection. So practically, what we want to do is to leverage the large graph and learn a single universal representation that can be used to improve multiple downstream graph applications. The reason we want to do this is because we will have a lot of savings. Imagine if you can have a single embedding that performs well on multiple tasks, practically, you save a lot of cost. You don't need to train for each of the specific tasks. You don't train a separate embedding. So you learn one embedding that performs well across the board. And this is practically some of the research we started 4 years ago, but we also extended this research to this to this paper that was published in the latest KDD on applying this language model GNN framework I showed you earlier on learning universal representation. So given a large graph corpus and multiple graph applications, we want to pre-train language models on the large graph corpus in graph-aware manner and even enhance various downstream graph applications. So imagine the large graph corpus we're talking about has the queries, the products, and you have multiple relationship types, right? Purchase, ads, like. And then we can imagine multiple applications. So for example, I want to predict ads, which ads to show in the Amazon web search page, right? So this is, I have a product, which ads to show for this product. Also, I want to predict for a query, which products to show, which products to recommend. So we have multiple downstream tasks. And you can see in this paper that indeed this framework allows us to train a single universal embedding and achieve a good performance across a variety of tasks at a very low cost. So this was one of the works we did, follow-ups of the LM-GNN framework. The other work we did was on actually how we can drop the cost of inference. Okay, so LM-GNNs are very, very expensive to run. So what does it mean? So the language models themselves, transformers, are parametric-heavy models, millions and even billions of parameters, millions in our case, and slow to run. And GNNs further exponentially increase the cost because of neighbor sampling, what I said earlier. So Bieber has billions of followers, right? So I need to solve this problem somehow. So practically, we have two sources of, let's say, latency, right? On the other hand, graph-free language models, which means graph-free language models means not language model GNN, but language model only, what the first model I showed you, are not effective on graph data. And this is what is shown in this task. You can see the accuracy of the models versus in the y-axis we have the accuracy of the model, in the x-axis we have the inference time. What we can see is that a GNN model takes 445 seconds to do inference, whereas a BERT model will take practically a much less inference time, but the accuracy, there is a gap, there is 4% gap. And this 4% gap can have like different impact on different applications, but it is something that we would like to close, right? And to that, we have Kostas, that is also in the audience today, Kostas Mavromatis, that led some of the research we published in the latest ECML. And how can we bridge this gap? And what we do to bridge this gap is to do graph-aware distillation. So distillation is practically a machine learning, let's say, concept, definition, right? That tells you how can you distill the knowledge of a teacher. A teacher is a powerful and very large language machine learning model, to a student model that is a smaller and efficient model. So the smaller and efficient model cannot perform so well as the teacher model that's very large and very large cost to run. But on the other hand, the smaller model is much more efficient. So what can you do? So practically what people do is they try to align the distribution, the output distribution of the teacher model to the student model. And practically they are trying to let the student mimic the teacher, okay? And this is the concept of distillation. So what we do in this work is we develop a method for graph-aware distillation, and we develop this model called Grad-BERT that, again, in this accuracy versus inference axis, you can see that it performs better even than the GNN model, so better even than the student, than the teacher, and you can read the paper for more details for this. And at the same time, the inference time is much better than the teacher, a little bit higher than the student. Or actually, I'm sorry. So the student is here, and the student is here, and the teacher is here. And this is the model we develop. So the model we develop has the same inference speed as the student, but at the same time has a larger performance. And yes, so this was about the concept of distillation. I would like to go into more detail in all of this, but I wanted to spend most of the time in introducing GNNs from scratch so that people have at least something from this talk. And if you want to read more, I urge you to read some of these papers I suggest here. And also a lot of the papers I saw in the introduction are very good for someone that wants to initiate in this field. So to conclude, we have a lot of ongoing research efforts on modeling text and image data with language models and GNNs, answering complex questions over knowledge graphs, designing GNN models for life science applications. Life science application means, for example, protein molecule design or RNA and gene modeling, active learning with GNNs, and also distillation using GNNs. And we have developed a lot of products in AWS and Amazon that are direct outcomes of the research I presented today. So thank you. And I want to leave some time for questions, if that's okay.
Yes. Start with some questions. So first of all, it's a great talk, and I really appreciate the effort you took to explain a lot of details. So I want to ask you actually some practical questions. So you mentioned applications to life sciences, especially if we talk about molecules and molecular generation. So, you can also describe them by sequences, and a lot of the successful methods actually are with sequences. So what is your experience? Do you have better methods that work with graph modeling?
So this is true. A lot of the successful methods are with sequences of molecule modeling, but also there has been value on graphs. The reason is that you can put this in a sequence, the molecules in a sequence, but the molecules have different bonds, right? So they have like the bonds of the molecules are not of the same type. And by capturing this heterogeneity, there has been some works that has shown some benefit. Go ahead, yeah.
Which works, for example?
I can share with you maybe with some papers. But the reasoning is that if you capture this more heterogeneous structure, you can capture more complex information. And also besides this, some of these molecules have a specific space, specific position in space, in 3D coordinates. So they are not simply a sequence like the words that come out of my mouth, but they occupy in 3D space specific positions. So the positioning of these kind of molecules can define practically a specific heterogeneous structure. So how far away is this molecule from that molecule, and what's the bond type of this that bonds these two molecules, if it makes sense. These two atoms, I'm sorry, not molecule, and they comprise a molecule. I think this is the reasoning behind this. Our research was more on how can we apply molecules to treat some kind of diseases. So we try to solve this link prediction problem in bipartite graphs. So on the left, you have molecules, on the right, diseases, and you have a knowledge graph that connects the two. So can you do this more better? But I can share some papers on molecule modeling on this.
Okay, thank you. Also, another question. So you showed the applications for buyers and sellers. And I know a lot of kind of mathematical models where you have different platforms and you have some assumptions of the buyers and sellers, and you want to kind of learn, if you have collusion or you have competition and know different effects of different parameters. And I wonder if you have interesting data set where someone can look at, different platforms and buyers and sellers and maybe not assume very strong assumption, but you use these data sets to infer some economic.
Yes, it's a very good question. So we have internal data sets that are actually we have a lot of internal data sets of fraud prediction, because fraud prediction is a real problem in Amazon. So practically sellers collude in order to promote the sale of their products. So they have some kind of, and also buyers even collude. We have a lot of internal data sets, but no public ones, if it makes sense. But this is a problem that can be indeed solved with graphs. And the reason is that the friend of my friend, has a similar behavior with me, right? This is the assumption that we are trying to solve with graph models. And practically, connections of colluders a lot of times also collude, right? Collateral of fraud, the connections of a fraud, a lot of times are also fraud. So, yeah, this is the underlying assumption of graph models in this case. Professor, yes.
Welcome back.
Thank you.
We'll enjoy the breadth of the problems you guys are working on. My question is on the slide before the last one. So we can challenge also. Okay. That one suggests that GNN is outperformed by Grad, right?
This is correct.
So question number one, did you try Grad GNN?
Costa, you want to take that?
Because that is basically what is inviting.
Yeah.
So Grad GNN.
Where does it lie?
On inference time. Sorry.
Go ahead.
Click. But we need to see the.
We don't have the.
So these are some slides I hide, right? Because there's too much context otherwise. But yeah, your question is right on the point, Professor. Because yeah, indeed, it is a little bit not intuitive to say that the teacher is outperformed by what we built, right? Because how can we build that? But the reason is that practically we have our finally distillation model will share here this parameter, which we call it Grad, okay? So, and the final output of this shared distillation will be Grad BERT. So this component, so this is our original teacher, and this is our original student. Typically, what people do in distillation is they have the teacher model, which is the upper component here, is not connected with the student model that is the down component here. So they are two different components, and you are trying to, the distillation tries to match actually the probability distribution data set of the teacher to the student. But what we do here is we have this model that is shared. So what does this mean? Is practically we will, during training and distillation of these two models, this model will be updated. So what we are saying is that the teacher can even be improved at the end of the distillation. So at the end of the distillation, if we compare, let's say, the BERT teacher, the improved teacher, let's say, the improved teacher with the original teacher, the improved teacher is improved. And the BERT, the Grad BERT is this component that is became more powerful.
Yeah, let me, because I know distilleries, but I don't know distillations.
Yeah.
But hold on. Is it related to meta learning or transfer learning? Or how is it related and what's different?
Yes, I can explain here in this slide what is the traditional knowledge distillation, but so
Transfers, okay.
yes, it is related to transfer learning. Okay. So practically we have this. This is the classic cross entropy loss, right? We're trying to output our prediction labels to the ground truth labels.
Okay.
But we have this lambda and this KL divergence loss.
So that's the regularizer. Okay.
Yes, so the KL divergence loss, I like this student and teacher, right? So this tries to output the probability distribution of the student and the teacher. We want this probability distribution to be close. That's why.
Clear.
Yes, so this is related indeed with transfer learning. But yes, go ahead.
So then my question is, so what I should do is do transfer learning across graphs and, stick with BERT if I want to do Grad BERT, or
Yes.
I don't have to go Grad GNN. That's what I'm saying.
Yes.
So, but back to your question before, so Grad, BERT, and BERT, if we look at the x
Yes.
axis,
Yeah.
if BERT has inference time x, Grad BERT has also inference time x.
Yes.
If GNN has inference time x, Grad GNN has also inference time x.
Yes.
So
But when we look at the y-axis,
Yeah.
so BERT has like accuracy y, Grad BERT is a little bit higher,
Yeah,
y
5.
plus delta y.
Yeah. I
And
understand.
the same would happen with GNN and Grad GNN.
Ah.
GNN has accuracy y, Grad GNN would have like accuracy y plus delta.
Yeah, but
Y
my
graph.
intuition says it will move to the right as well. It will have delta x and delta y, and the issue is how much on whether should I bother with Grad?
Yeah, so
GNN.
the inference time would be the same. So you get this with Grad GNN, you get higher accuracy with the same inference time.
But you look at the BERT and Grad BERT. The Grad BERT is to the right. It's 34 versus 218.
yes, so this is why I think it's confusing the system. So I'm sorry for this, because this BERT. So okay, everything that is yellow is BERT, but they are BERT models of different size. So the triangle BERT and the triangle, this and this are the same size models. This and these are the same size models,
Okay.
and this and these are the same. So yeah, maybe I should remove all of this because
I understand, I think.
sorry for this. Yeah, so just like forget this and like consider like this and this and this. Yeah. So yeah, thanks for the question and for the pointers to improve slides. Costa, take the notes.
A question from Paul.
Yeah.
Maybe you can click on the Zoom link and see the question
Sure.
yourself, otherwise I can read it.
Wait a second.
Okay, so
QA. Yeah. Thanks for the.
but can you click on it that everyone can see it? If you click on the Q&A,
I can read it out loud.
oh, okay, there's a way to share it to everyone, but okay. We can summarize it, yeah, it's a long.
So the question is about long documents, and the question is about what would be good candidates for linking paragraphs and longer context and longer context, right? So
Thank you.
yeah, so I think first of all, maybe you can come on the speaker, because I think that I would like some clarifications. But from what I understand, is the question about how can we model a long document as a graph?
Check and see if I can have him.
Yeah, so I think the question is how can we model a long document as a graph? So practically, you can imagine you can imagine a long document practically as a graph, and you can connect this long document across different paragraphs. If, for example, a paragraph mentions the same entity across different components. So, in fact, actually, some of this work, I personally have never worked in this field, but I have read some works practically that try to do this, and I can share it with you. If you want, please send me an email. But practically, what's the intuition behind that is that if you have a very long document, these transformer models that we just explained struggle a little bit, because actually their input to this transformer has to be up to 512 tokens. So 512 tokens is like, let's say, a really long paragraph, but cannot be a very long document. So what does it mean? So how can you encode a very long document into a single vector? So there are a lot of approaches. Some people would do it with like a lot of inferences, but some other people have tried to connect paragraphs that are related and form the graph and then apply GNNs. Yeah, I think this type of methods can be applied there as well, and there have been some works I can share with you.
Thank you.
Thank you.
Thank you. Cheers.
So he was happy with the answer.
All right.
Any other questions?
Yes, please.
Have you guys, so for the product review graph neural network pipeline, have you considered adding like a image encoder as well to this?
Yes, that's a very good point. In general, yes, we are considering adding image encoders. The only problem is scalability, because, for example, each product has like, say, 10 images, and we have like millions of hundreds of millions of products. So this makes the problem much more complex. So we need to understand what is the value added by adding this type of encoders, but this is a direction we are trying to understand. Yeah. Please.
Yeah, I have a question. I was interested in how this can be applied to items that have multiple features, as you explained in the very front when you're explaining GNN. The first one is, so when you do this graph-BERT, is it able to take multiple features? And what happens if the types of feature each items consist is different, or like many of them exist as null features in them?
So you're asking what happens if we don't only have text as an input, but also other features?
Yeah.
So in the model that we have developed here is about text. But if we had other features, imagine you would have some other pipeline here that says, for example, the age of a person, the education level, and this and that. And this will be encoded into vectors that will be feeding into an MLP layer that would be here, and will merge these things. Like, so you can extend this type of architectures to account for this, but the focusing in this work was more about how can we solve text features. But you can extend this type of work, yeah. Yes.
Okay, I need just to check one thing, because usually we have meeting with students right after the talk, and
Yes.
it's impossible. 3 p.m. is still okay for you to meet?
For me, it's okay.
Okay, so students who want to meet with him and get career advice can come at 3 p.m. to LIND 402. Okay, so it's just next to your office. Any other questions or? Yeah.
So I had another question. So if you have like a terrible description, like they just like select every word out of the dictionary and throw it in there. Like, and you know, it's like, say it's a garden gloves and they say it's a garden trellis, you know, nursery, greenhouse, etc. Things that are totally unrelated. How does can your model account for and extract the relevant information, or does that just kind of go to like a noise garbage category?
Yeah, no, I think that this could be adding too much noise in this type of models, and yeah, the encoding it's very crucial to encode the correct mapping of the words, right, all of the phrases. So this is a very crucial step. Yeah. Okay. Thank you.
Thanks again. Great.
For the invitation.
Like 40 people.
And if they want, one of the reviewer is not from. Very good. How many people have? Always join. The inverse is 16. So 8 is for accept.
One more step.
But you know, in your it gets rejected.